Well, a warm welcome indeed. Thank you for being here, everybody. Go ahead and get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to continue our use of the difference quotient and a limit with the difference quotient to find the derivative. We're going to find some derivatives. Just a reminder, last time we took a look at the derivative of x squared in order to find the slope of the tangent line. That's the line that touches the graph at a point and sort of continues on with the same slope while the function is changing its slope. We use this difference quotient definition, so make sure you are familiar with that definition of the derivative, because we're going to use this in some examples today. And the examples we cover are some of the types that you might encounter in the first test, maybe in a calculus class where you have to do these sort of derivatives the long way. You guys will learn that there's a shortcut way, which is going to be used for the remainder of the course. It's much nicer, and you'll ask yourself, why didn't we just do this from the beginning? It's because we wanted to set up a little bit of foundational understanding before we just tell you these quick rules to do. That would kind of rob you of learning the calculus. It would just show you how to push some buttons and turn some knobs and get a correct answer. That's not really what the point of learning math is. So without further ado, let me give you a glance at these examples. You should leave plenty of space. In fact, I don't even think I left enough space here. You should leave plenty of space, because when we simplify, we're going to have to do things step by step by step. And you might remember that from the example in the previous video, that we had quite a few steps. We had to keep writing this limit word over and over. We're going to have the exact same situation here, except these are arguably going to be even longer because we have to do some algebraic manipulation. All right, let's get started here. So if we want the derivative, which represents the slope of this graph, we're going to say f prime equals the limit as h goes to 0. Reminder that h is the gap between the two x values. F of x plus h, that's like my y2, minus f of x, that's like my y1, over x2 minus x1, which is simply the gap, h. Okay, but what is that going to look like for this function? Well, we already have f of x. If you just plug an x in, that's what you get. But what is f of x plus h? Well, all you have to do is plug in x plus h instead of x. Like that. Okay, so really we're trying to find the limit as h goes to 0 of this thing, which I will duplicate and drag over here, minus this thing, which I will do the same. Get over here. Of course, if we try to plug in h goes to 0, we're just going to get the same thing minus itself on top, over 0, 0 over 0. That's no good. So here is the first type of algebraic manipulation that we have to do when we're involving a radical expression or radical function. Well, we want to break these radicals. We also want to cancel the h, but the method that we're going to use focuses on canceling these square roots by multiplying something on the top and bottom. Can anyone guess what that is? Maybe you can. We're going to use the conjugate. I do have a video about simplifying radical expressions. You can check that out if you want a little bit of a refresher. But what the conjugate does, or what it looks like, I should say, is it looks exactly the same. I call it the evil twin, x plus h minus 6 inside, and still have this square root x minus 6. But the difference, what makes it the evil twin, is that the symbol in the middle is switched. So this is a plus, and we have to multiply on the top and bottom. Otherwise, we're unbalancing this fraction artificially. We're not allowed to do that. But we are allowed to multiply by, I'm going to get away with this quote-unquote quotation marks, we can multiply by 1. Not to suggest that this isn't actually 1. Anything divided by itself is 1 other than 0. But it doesn't really look like a 1, right? We got some stuff on top, some stuff on bottom. Since it's the same stuff, we're basically just multiplying by 1. And why did we want to use this? Well, you can watch the conjugate multiplication video or the radical expressions video if you need to. But the short story here is that we're creating a difference of squares. You see that? We have like a minus b and a plus b. When I FOIL that, when I multiply it all out, I'm going to get something rather nice. Because I'm going to get a squared, which just breaks the square root here, leaving me with x plus h minus 6, minus b squared. Same thing happens with this b term. They're going to cancel the square root. Don't forget your parentheses. That's the most common and silliest mistake you can make here. And then on the bottom, do not distribute. Okay, so I want you learning these couple of techniques. That's the conjugate multiplication for simplifying a radical expression. Use parentheses whenever you're subtracting some kind of quantity. Make sure you're putting parentheses. And then on the bottom, the hint is to not multiply the h into the parentheses. Why not? Because the whole point of this exercise is to cancel the h. And if I go stuffing it in the parentheses, now I'm going to have h's inside the parentheses in 2 terms. I do not want that. In fact, just take a look at what happens on the top here, yeah? Limit as h goes to 0. Well, x, that cancels with a minus x. And negative 6 cancels with a minus negative 6. So that just leaves me with an h on top. And this is why we did not want to multiply the h on the bottom into the parentheses. Yes, because we're going to cancel the h's now. That was the problem the whole time. That was why we couldn't plug in h goes to 0. It was causing some kind of 0 over 0 situation. But now that we're not worried about that, we can go ahead and plug the limit value in with no issues. So now we don't have to write limit once we've plugged in the value of 0. And this is going to be 1 over, well, this is root x minus 6 plus root x minus 6. So there are 2 of those. Why don't we call that 2 root x minus 6? That is your derivative. Reminder of what the derivative means. That means that the slope of the original function's graph, the square root function, the slope of that can be determined with this new equation. It's like a new function called the derivative. Okay, that's kind of the basics. Let's do another example with a different situation. The situation we have here is called the rational situation. This is a rational function because we have a variable in the denominator. So let's just write out what f of x plus h is. You know we're going to have to use that. Just plug in x plus h. That's going to give us negative 4 over x plus h. Okay, so that means the derivative f prime equals to the limit as h goes to 0 of negative 4 over x plus h, right? That's f of x plus h, minus negative 4 over x. You already know what I'm going to say about these negatives, right? Be careful with them. I would not necessarily recommend multiplying it right away. First, just get used to writing the structure out, and then in the next step, feel free to multiply it. So how do we deal with this? This is a new situation. It does not involve a radical. Well, we're basically just combining fractions. So how do we combine fractions? Really simple, right? To combine fractions, we simply need a common denominator. Let's extend this a little bit. So just get a common denominator. How would we do that? We have to multiply this one by x plus h on top and bottom. And we have to multiply this one by x on top and bottom. And I put parentheses around it so that it's clear that x is multiplying to the entire denominator there, not just to h. Okay, so this is going to become limit as h goes to 0 of negative 4x. Now we can make this plus 4x plus 4h over the common denominator of x plus h. Now that's just what's going on up here. this is still all over h, which we will fix in the next step. We'll do some canceling because 4x obviously cancels with negative 4x. Yeah. 4h over x times x plus h. And then I'm going to take that bottom h here. I'm just going to flip it so that it doesn't look like a fraction on top of another fraction. And ooh, voila. We see that the h's are going to cancel there. So the goal in a lot of these situations is just to cancel that pesky problematic h. This is going to be x times x plus h. Now we can plug in the h value. We don't have to write the word lim. This is just going to be x times x plus 0. I guess it's just x. So 4 over x squared. That is the derivative, which means if we plug an x value in, it tells us the slope on the function. If we want the actual function value, like where's the y value on the graph, we need the original function. But if we want the slope at that point, we need the derivative function. That's kind of how it operates. Okay, that one was actually pretty quick, right? Because there's just one simple rule that motivates our process, combining the fractions, as opposed to knowing that the conjugate is like convenient here. Well, let's mix those two worlds together. See what you do here. If you want to pause the video and give yourself a shot to try this, I highly encourage that. I think any great student is going to do that. So just think about that. Let's see, the derivative f prime is the limit as h goes to 0 of 1 over square root of x plus h, because that's f of x plus h, minus 1 over square root of x. And this doesn't look as complicated. It's not like a huge monster of a problem, but you have to think about what principles we're going to go with first. And there's an easy way and there's a hard way. I'm not saying it's impossible if you go down the wrong route, but it's just not really feasible for this level, I think. Or maybe it is. I just took a sip of my coffee, so maybe I'd be able to power through it. But in case you're curious, which method should we go with right now? I personally think the best method for this is to use conjugate multiplication. So what I would do here is I would multiply this entire top expression by 1 over square root of x plus h plus 1 over square root x over itself, of course. 1 over square root of x. Now again, in the bottom, do not multiply that out. What we're using this for is to conveniently simplify the top into a difference of squares. So this is going to become the limit as h goes to 0, breaks the root 1 over x plus h, minus breaks the root 1 over x. So now you see it really does become a lot like the rational situation, but there's this extra thing going on here, right, where we have this thing in the bottom, plus 1 over square root of x. So it's kind of like the rational situation that we just did in a previous example, but it's a little bit different because we have this extra thing in the bottom, right? This was not here when we did the previous example. We did have, where is it? We did have all this, the negative with the fraction x plus h, and then with the fraction just x. We had that, just like we do here, fraction x plus h, fraction x, but we have this extra thing on the bottom. So what do? Anything special? Nah, we just trust the math. We need to combine these fractions together. So what are we going to do? We're going to multiply this by x plus h on x plus h, and we're going to multiply the other one by x on x. There we go. So this is limit as h goes to 0. We have x minus x plus h all over the common denominator, x plus h. And then all of this is over h plus this kind of weird extra term here. But I will say this is not a problematic extra term. Let's just observe that that's not going to cause a problem. When h goes to 0, there's no problem in here. It just becomes x in the root, and you can add those two things together. So we're not going to have an issue with that. We are going to have an issue with this h. That's why we're doing what we're doing, so that we can cancel the h on top and bottom, just a factor of h on top and bottom. So here we have x minus x, that obviously cancels, and then we have negative h over x plus h. Then I'm going to flip this to 1 over h, and then I'm also going to flip this separately. I know it's going to look weird. 1 over root x plus h plus 1 over root x. I know that looks a little funky, but just bear with me here because, like I said, it's not going to cause any issues when we try to plug in 0. So let's go ahead and plug in 0. I know it's a little sloppy right now. X times x plus 0 times, this is all just 1 now, so it just kind of goes away. 1 over square root of x plus 0. Oops. 1 over square root of x plus 0 plus 1 over root x. This does simplify in some way. This is negative 1 over x squared times 1 over 2 over root x. Okay, that's looking a little messy, but we'll still put it together here. Let's see, this is going to be x squared times 2x to the negative 1/2 power. See that? Because this radical is in the denominator, and it's a square root, so it's a negative power and a 1/2 power. And if we combine these together, these powers here of x squared and x to the minus 1/2, add the powers together and we get x to the 3/2. So that's kind of a weird derivative. You could also write it as negative 1/2 x to the negative 3/2 if you like. You could also write it as negative 1 over 2 square root of x cubed. These are all acceptable forms, but really the tricky part is getting there with the limit process and algebraic manipulation. All right, so those are 3 hefty examples. I think they're really good types to look at because these are some of the types that are considered a little harder when you're learning how to do limit definition of the derivative in calculus. And oftentimes on an exam, they'll throw 1 or 2 of these types of limit derivatives on the exam just because it's kind of tedious and you have to be careful with your procedure. And so it's a pretty good test of those skills, right? Well, I think that's enough blab out of me. I hope you guys really learned something about limits and derivatives. Over the summer is a great time to continue working because as soon as you stop using it, you start losing it. I'll see you guys next time.